we have discussed the two important rules for the Ternary construction in the ternary phase diagrams. In this class, I am going to talk about the remaining rules. The third important rule is that in a isothermal sections, ternary tie lines will never intersect, correct. So, why it will never intersect? Let us see the problem. Before I talk about the problem, in a ternary system, the Gibbs phase rule says so for a two phase zone like alpha plus liquid or liquid plus solid, degrees of freedom is equal to 2. There are 2 degrees of freedom, right. It is a bivariant system. That is very simple. If I know that the degrees of freedom is given equal to C minus P plus 1, there are 3 components of C is equal to 3. So, in the 2 phase region, there are 2 phases solid plus liquid. So, there are phase number 2. So, 3 minus 2 plus 1, so that is equal to 2. So, it is a bivariant system, please remember that. Now, if suppose let me just I will just go back to the board and explain it. Okay, so it's very convenient. So, if I suppose draw this is my liquid plus solid zone L1 L2 S1 S2. Okay. So, now I draw one tie line L4 S4. Okay, this is S4. Let me draw it properly. And I draw another tie line which is L5 S5. These are the 2 tie lines which are drawn. Now, suppose I draw a tie line in such a way that it intersect L6 S6, okay, it intersects. This construction is very clear to be understood. So, initially I draw a tie line L4 S4, another one L5 S5 which are not intersecting. Now, I draw a tie line L6 S6 which intersects L5 S5 tie line in such a way that these ends meet at S4. Now, according to this tie line L4 S4 and L6 S6, there are 3 phases which are at equilibrium. L6 composition liquid phase, solid phase S4 composition and S6 composition. 3 phases are in equilibrium according to this construction. You might be wondering why. Very simple. Tie line connects number of phases from one end to the other end, right. So, therefore, if this tie line L6 S6, they are actually connecting the solid and liquid phases, one at L6, other one is as S6, then and it is intersecting with L4 S4, that means what? L6 S4 S6 3 phases, 2 solid and 1 liquid phases at equilibrium. And as I told you just few minutes back, this is a 2 phase equilibrium zone. So, degrees of freedom is 2, but if 3 phases at equilibrium, degrees of freedom will be 1. So, this will violate the Gibbs phase rule. So, in the sense, basically I can tell that tie lines inside this isothermal section will never intersect with each other. If they intersect, this will violate the Gibbs phase rule. So, this is the rule number 3. The tie lines in isothermal section will never intersect each other. Now, the fourth one, the most important rule for which I need to spend a lot of time is known as Konovalov rule, rule 4. Very important rule, Konovalov's rule or rule 4. Why it is important? I have been telling you only qualitatively that tie line will rotate from one binary to the other binary. Okay. Tie line extended will never meet the corner, tie line will not intersect, but this rule will tell you how it will rotate, how much it can rotate, all this stuff. Well, this rule says, let me just tell you exactly what is that. Tie lines rotate in a counterclockwise direction, as the temperature falls. Temperature will fall, right, from T1 to T2 to T3, T4. So, tie lines has to rotate. So, tie lines will rotate counterclockwise direction as the temperature falls, and this rotation is coincides, this rotation will coincide with the fall of temperature from C to B to A here. So, temperature is falling which way? C has the highest melting temperature, followed by B, followed by A. So, temperature is falling like a counterclockwise direction, C to A to C to B to A. This is a counterclockwise. If you look at the triangle C to A to B, it is a counterclockwise direction. That is why I say tie lines will rotate in a counterclockwise directions as the temperature falls, and this rotation coincides with the direction from the highest melting temperature to the lowest melting point component. So, what is it? Let me just explain it. It is very simple. Okay. As you know, this is because solid is always richer than the melt in the primary component. So, suppose solid C, solid here, solid is rich in C than the liquid. That is very simple. Liquid is more lean in C than the solid. So, if that is the case, I can write down, that means what? I can always, well, let me just tell you this way, solid is richer than the liquid, which is in equilibrium is in that component. So, suppose solid is in equilibrium with component C. So, this will be richer in C than in the liquid. So, in a nutshell, I can write down this way, XAS, suppose it will be also always XAL, right, and I know that XAL, XAS plus XPS is equal to XAL plus XPL equal to 1, correct. So, therefore, XAX divided by XAS plus XPS is greater than equal to XAL divided by XAL plus XPL. That is nothing but dividing these two things by 1, right. So, I can also write XAS divided by XAS plus XPS minus XAS greater than equal to XAL plus XPL minus XAL. You might be wondering what is this? Well, very simple. If I reduce the denominator, the fraction value will increase, right. So, and here I am reducing denominator in such way that XAS is greater than XAL, correct. So, therefore, this will remain valid. So, now I can write down XAS is equal to X divided by XBS greater than equal to XAL divided by XPL. This is what is your Konovalov's rule. So, that because of these, the solid in which it is in equilibrium will have higher concentration A than B compared to the liquid, and if this is true, then the tie lines will rotate the way I said you. Tie lines in this case, our case, rotating counterclockwise direction as the temperature falls, because the solid which is in equilibrium with the liquid is always richer in the component which is higher melting temperature, correct. Solid which is a higher melting temperature, solid which is in equilibrium with liquid will be having more component which is a higher melting temperature. In this case, our case, solid will have more C than the liquid, because C is the highest melting temperature, and because of that tie lines will rotate in the rotation of tie lines will coincide as the melting temperature falls from highest to lowest. So, melting temperature is falling, How? Momentum is falling from C to B to A. So, because of this melting temperature fall in this counterclockwise direction, tie lines also rotate in the counterclockwise direction. So, this is what exactly I just wanted to tell you. Now, one can actually do these things in a much better way. What is that? Well, let me just do this construction. No, let me just draw a arbitrary tie line like this. This is S1, L1, and the alloy composition is X, okay, or letter SL like that. Now, I join and extend this. So, this becomes S1. I join these 2 points C and X and extend this become X1. I join these 2 points, extend this, it become L1. Okay. That is what I have done. Very simple. I have this tie line LS. I am joining the point S with the corner C, joining the point X with the corner C, joining the point L with the corner C, and extending, so that it meets on the AB things. So, now this is the angle theta, it extend with the point with the line connecting X and C and extended, correct. So, I need to see whether this angle rotation is exactly proper or not in a real sense. How do I know that? That can be done using Konovalev's rule, the same concept. So, how it is done? Let me just take the book and do it for you, because sometime also I forget. Okay, or rather I can do it with this. Well, so erase this part. Well, as you see here, XAL divided by XCL here is equal to what? XAL is equal to what? L1A divided by AB, right, because I have extended then and it is hitting here. So, L1A is what is your A, L1A or L1C, yes, LO, oh sorry, I made a mistake, better to keep this, that is what is always happens. So, let us just change these coordinates A, B, C. So, XAL is L1C divided by AC. Similarly, XCL is what? L1A, sorry, L1A divided by AC. Okay. So, that is why I have written XAL divided XCL is equal to L1C divided by opposite arms L1C divided by L1A. So, again XAS divided by XCS, S means solid, L means liquid, is equal to S1C divided by S1A, S1 is here, S1C divided by S1A. So, as you know that S1C here S1C divided by S1A is greater than S1C divided by S1A is greater than L1C divided by L1A. So, that means what? XAS divided by XCS is greater than in equal to XAL greater than by XCL. So, I follow the Konovalev's rule, this is the Konovalev's rule, I follow that same rule. So, I change the orientation of this tie line and I check by using Konovalev's rules. You might be thinking how exactly measure this angle theta. Well, that cannot be measured using Konovalev's rule directly, that has to be done using experiments. So, one has to do experiments with liquid of composition this, solid of composition this, and find out these two composition points, but at least it says which way it is going to rotate it. As you see here, this is anti-clockwise rotation from B to A to C. Here actually B has a higher melting temperature than A and C. So, that is what is actually the Kornewallop's rules concept. So, Kornewallop's rules actually is very important in the sense that it tells you the orientation of these tie lines, also it tells you even the directions of the rotation of the tie lines, the temperature drops from liquid from highest to lowest melting temperature the components. So, as the temperature drops, it tells you the things. So, these are the two important rules I told you. So, these 4 important rules I will tell you. There is a 5th rule, but it is not so severe, not so serious. All these rules are nicely written in this book, and I do not need to do that. Again further, if you have any questions, you can either follow this book or the other book which I have given, otherwise one can actually look into that. So, now I am going to talk about, because we need to discuss, we have discussed only the isothermal sections, we need to discuss also the projections of the solidus and liquidus and the vertical section and polythermal sections. So, as you know, we can actually also project these solidus and liquidus surfaces on the at different temperatures onto the Gibbs triangle, and this is exactly shown here. So, this is what is your solidus liquidus surfaces, and now if I take sections at different temperatures T1, T2, T3, T4, T5, T6, T7, T8, and I can plot them. Okay, let me just tell you what is that. It is not there, okay, otherwise I can draw it and show you. So, they are very simple, let me just draw it. This probably I could not add into the slides. So, I have only discussed you the isothermal sections, and then the tie line concept came, and that is what we discussed detailed. There are several more projections possible. Another one is the second projection is the liquid and solid surfaces can be projected onto the triangle. So, suppose I have 3-dimensional model and I want to project solidus and liquidus surfaces. So, at different temperatures. So, I am projecting, this is liquidus solid line and this is solidus. Please remember these are done at different temperatures. This is at T1. So, L1 S1, so L1 L2 and S1 S2. Let me just draw. So, then this is S1 S2, this is L1 L1 better, S1 S prime. This is L2 L2 S2 S2 prime, L3 L3 prime, S3 S3 prime, L4 L4 prime, like that. So, basically these are what? These are different sections. In one section I am drawing like this. So, these same things are projected on the Gibbs triangle at different temperature. This is suppose at temperature T1, and then I draw another one So, I am drawing these different sections 1, 2, 3, this is at temperature T1, this is at temperature T2. I am drawing these sections at different temperatures, and then all the sections are projected onto the Gibbs triangle, all of them. That is what is the liquidus and solidus surface projection, it means. So, what it means? It means that I take this, I draw these triangles at different temperatures at T1, T2, T4, T4, T5, T6, T7 or T8, whatever different temperatures, and then I can get these sections at different isothermal sections, and then all these isothermal sections are projected onto the Gibbs triangle. That is what I am doing. So, as you understand step by step way, first thing I did, I took one section, isothermal section. How I have done that? I have taken a triangle at the temperature T equal to T1 parallel to the Gibbs triangle and just pass it through the phase diagram, 3-dimensional model. And because I pass it through 3-dimensional model, it cuts the liquidus surface at 2 points L1, L1 dot and solidus surface at 2 points S1, S1 dot or S1 prime, right. So, because now, so this becomes my projection of the solidus and the liquidus surface at temperature T1. I can do the same thing at temperature T2 and subsequently lower temperatures. Once I get all of them, I can put all these sections, this is actually each a triangle, on top of each other. Once I do that, I get this diagram. This is nothing but liquidus and solidus surface projections. Understand? So, at different temperatures, whatever section I get, I plot it to the projections. This is very important. Why? Because this tells you how the liquid and solid surfaces are changing as a function of temperature. Here actually they are not changing at all, because it is a isomorphous system, therefore there is no change, but it might be possible in some diagrams this will change, and this one will allow us to know how this orientation is changing. That is what I wanted to convey. So, in this class, in a nutshell, what have I told you? I talked about you all the rules and regulations of the tie lines for the isothermal sections, and as a projection formalism, I tell you how to project liquid and solid surfaces onto the Gibbs triangle. In the next class, I am going to talk about two important projections. One is the vertical section, other one is the polythermal sections. Okay. And subsequently, we will go forward looking into the how the solidification of the ternary alloy will take place. We will discuss about that. Then finally, we will move to eutectic systems. Let us stop it here.